In section 8.3, we're simplifying radical expressions. Our objectives are to use the product rule and quotient rule for radicals, simplify radicals, simplify products and quotients of radicals with different indexes, use the Pythagorean theorem, and use the distance formula. In this section, we develop rules for multiplying and dividing radicals that have the same index. The square root of 25 times 9 equals the square root of 225, which equals 15. This can be written as the square root of 25 times the square root of 9, and the square root of 225 is 5, the square root of 9 is 3, so we get 5 times 3 is 15. This is an example of the product rule for radicals. The product rule for radicals says if the nth root of a and the nth root of b are real numbers, and n is a natural number, that's the index of the radical, then the nth root of a times the nth root of b is equal to the nth root of a times b. In other words, the product of two nth roots is the nth root of the product. Let's look at example 1. We have the square root of 6 times the square root of 5. We can write this as a single radical, the square root of 6 times 5, and then we can write that as the square root of 30. The second example is the square root of 13ab times the square root of 2c. We can write this as a single radical as the square root of 13ab times 2c. We can simplify this radical by multiplying 13 times 2 to get 26abc. For example 2, we have the cubed root of 4 times the cubed root of 11. We could multiply these together because the index of each of those radicals is the same. So we can write this as the cubed root of 4 times 11, which then we can write as the cubed root of 44. On the right side, we have the sixth root of 15x to the third times the sixth root of 5xy squared. We can write this as a single radical with the same index, and we get the sixth root of 15x to the third times 5xy to the second power. Now we can simplify what's under the radical as the sixth root of 15 times 5, which is 75, x to the third times x to the first power is x to the fourth power times y to the second. Now look at the example at the bottom of the slide. We see that the cubed root of 9 times the fourth root of 5 cannot be simplified using the product rule because the indexes are different. Caution, use the product rule only when the radicals have the same indexes. The quotient rule for radicals. If the nth root of a and the nth root of b are real numbers, and b is not equal to 0, and n is the natural number, where n is the index of the radical, then the nth root of the fraction a over b can be written as two nth roots, the nth root of a in the numerator over the nth root of b in the denominator. In words, the nth root of a quotient is the quotient of the nth roots. We will be looking at simplifying radicals, and we need to consider the following conditions. Number 1, the radicand has no factor raised to a power greater than or equal to the index. Number 2, the radicand has no fractions. Number 3, no denominator has a radical. And number 4, the exponents in the radicand and the index of the radical have a greatest common factor of 1. Let's look at the following examples. The square root of 81 over 16 can be written using the quotient rule for radicals. And we can write this as the square root of 81 in the numerator over the square root of 16 in the denominator. Then we can simplify that as the square root of 81 is 9 and the square root of 16 is 4. So we can write our final answer in simplified form as 9/4. In the second example, we have the square root of 11 divided by 49. Let's write this as the square root of the numerator, 11, over the square root of the denominator. Now we can simplify this Although the numerator cannot be simplified, the square root of 11, since 11 is a prime number, has no perfect square factor, and the denominator is the square root of 49, which is 7. We can write our answer in this form, the square root of 11 divided by 7. It's considered to be simplified because the denominator does not have a radical in it. The third example here, we have the cubed root of negative 27 over 8. Let's break this up into two cubed roots using the quotient rule for radicals. We have the cubed root of, we'll put negative 27 in the numerator, bringing that negative that's under the radical to the numerator, and dividing that by the cubed root of 8. When we simplify the numerator, the cubed root of negative 27 is negative 3, and the cubed root of 8 is 2. So this is our answer in simplified form. Finally, in the last example on the page, we have the opposite of the fifth root of y to the 10th over 243. Let's simplify this using the quotient rule for radicals. We can take the fifth root, actually keep that negative out in front, the fifth root of y to the 10th in the numerator over the fifth root of 243 in the denominator. Keeping that negative out in front, we get the fifth root of y to the 10th. Well, y to the fifth root of y to the 10th, if I do this over here, so you can see that the fifth root of y to the 10th is the same thing as y to the 10th raised to the 1/5 power. So this radical can be simplified, and as well as the fifth root of 243, that can be simplified to 3. Recall that 243 is the same thing as 3 to the 5th power. The numerator can then be simplified the y to the 10th to the 1/5 power, that when we multiply the power times a power, we get a negative y to the 2nd power in the numerator over 3. And we can write this as our final answer. The simplified radical is negative y squared divided by 3. Now let's look at some other radicals that don't turn out to be nice whole numbers. We can still simplify the radical by factoring what's underneath the radical and finding any perfect squares or perfect roots that are factors of the radicand. Beginning with the square root of 28. The square root of 28 we can write as the square root of 4 times 7. When we factor 28, that is 4 times 7. So then we can break this up into two radicals, the square root of 4 times the square root of 7. And because the square root of 4 ends up being a nice whole number that can be simplified, we can write this as 2 times the square root of 7. Another way to look at simplifying this radical is to create a factor tree. We're trying to simplify the square root of 28. And suppose ideally what we're doing is looking for that perfect square that can be a factor of the radicand when you're finding square roots, simplifying square roots. So what you could do is begin taking the radicand of 28 and factoring it. We know that 28 is an even number, so you can write it as 2 times 14. Now 2 is a prime number, so we're going to keep that, but 14 can be further factored into 2 times 7. These are all prime factors. Since we're finding the square root of 28, that's the same thing as taking the square root of 2 times 2 times 7. With the square root, the index is understood to be 2. So in this case, we're looking at perfect pairs of factors that will come out as a single term. 2 times 2 is 4, and the square root of 4 is 2. So we can write this as a 2 out in front and a 7 under the radical. So anything, when you're looking at simplifying square roots, you're looking at pairs of factors that are pairs, and we can take out any factors that are considered to be twins, and that factor comes out in front. All right, in the next example, we have the square root of 6,125. Ideally, you want to find the largest perfect square that is a factor of 6,125. That's not always so easy to determine. So let's create a factor tree and find out how we can simplify this radical. Now 6,125 ends with a 5, so I know that 5 is a factor. So this can be written as 5 times 1,225. Now this 1,225 also ends with a 5, so we know 5 is another factor, and that's the same thing as 5 times 245. And again, that ends with a number 5, so we know 5 is another factor, so we can write this as 5 times 5 times 5 times 49, and 49 can be factored as well. So let's continue it over here. We have 5 times 5 times 5 times 49, which can be written as 7 times 7. So we're taking the square root of these factors, and since a square root has an understood index of 2, we're taking out pairs of factors that are identical, those identical pairs. When we simplify this, the identical pair 5 times 5 is really 25, and the square root of 25 is 5. So even though they're paired together underneath the radical, when they come out in front, it becomes a single 5. The 7 times 7 is 49, and the square root of 49 is 7. So a single 7 comes out in front. Now this 5 that's not part of a pair, it's not part of a perfect square, that 5 is going to stay under the radical. So then we can simplify this so that our final answer can be written as 5 times 7, which is 35, times the square root of 5. This is the final answer in simplified form. Another way of looking at this problem is if you were to start off with factoring out 6,125, knowing that it can be factored as 125 times 49, and then 125 can be factored as 25 times 5 times 49. Now that 25 and 49 are perfect squares, you can simplify that by writing this as a square root of 25, which is 5, the square root of 49, which is 7, and that 5 is left over under the radical without any other pair. So that stays under the radical, and then finally we simplify to 35 times the square root of 5. All right, let's look at the third example here, the fourth root of 25. Now we know that 25 can be factored as 5 times 5, but you can't break it down into any other factors, any other prime factors, that is. And when we're looking at the index of 4, we want to take out perfect powers of 4. If there were 4 repeated factors of 5, then it can be simplified. Since there's only 2 and the index is 4, we don't have enough to simplify this radical. So we say that this cannot be simplified. Let's look at the bottom example here, the cubed root of 128. Let's make a factor tree, and this time with the index of 3, we're looking at perfect cubes, or triplets when we create the factor tree. 128 can be factored as 2 times 64, and 64 you can factor further into 8 times 8, and 8 can be factored into 4 times 2, as well as the other factor of 8 is 4 times 2, and then each of those factors of 4 can be factored into 2 times 2. Alright, so this really could be factored as the cubed root of 2 times 2 times 2 times 2 7 times. And when we are finding the cubed root, we're taking out triplets in this case, triplets here. 2 times 2 times 2 is 8, and the cubed root of 8 is 2. So that comes out as a single 2 in front of the radical. And another single 2 comes out in front of the radical. And this 2 that's left over that's not part of a triplet stays under the radical. Then we can simplify this as 2 times 2 that came out in front becomes a 4, and the cubed root of 2 stays under the radical because 2 is not part of that perfect cube. So this is our answer in simplified form. All right, let's simplify 2 radical 72x to the third. Let's simplify 72 by finding the factors, creating a factor tree, and we know that 72 is 9 times 8, and 9 is a perfect square, which can be written as 3 times 2, and 8 can be, 3 times 3, and 8 can be written as 2 times 2 times 2. Because this is the square root of these quantities, we're taking out perfect squares. The x cubed can be written as x times x times x. Again, when we're simplifying the square root, you're taking out pairs. So what we have out in front already is the 2. Now in front of the square root, we can write the square root of 3 times 3, the square root of 9 is 3. We can bring a single 3 out in front. The 2 times 2 is 4, square root of 4 is 2. It comes out as a single 2. This x times x is x squared, comes out as a single x. And then anything that's left under the radical, the 2 and the x, will stay under the radical as 2x. Now we simplify what's out in front. 2 times 3 times 2. 6 times 2 is 12. We get 12x radical 2x. That is our simplified radical. Let's look at the cubed root of negative 54x to the third. Well, negative 54 can be written as, using a factor tree here, is 9 times 6, a negative times a negative times 6, and 9 can be written as negative 3 times 3, and 6 is 3 times 2. Now, because this is a negative and it's a cubed root, we can take out triplets here in terms of the radical. Negative 3 times 3 times 3 times 2 can also be written as negative 3 times negative 3 times negative 3. So that would give us the cube, the triplets in terms of simplifying the cubed root. We also have the x to the third, which can be written as x times x times x, and that would be a triplet that can be simplified in terms of the radical. So we have the cubed root of the factored form of negative 9 times 6 times x to the third, and then simplifying again, factoring, creating that factor tree. Now our answer will be written as a cubed root. This negative 3 times negative 3 times negative 3 will come out as a single negative 3 in front of the radical. This 2 that's left underneath the radical is not part of a triplet, so that's going to stay underneath the radical. The x times x times x, that's part of a triplet. The cubed root of x to the third is a single x. So our answer in simplified form is negative 3x times the cubed root of 2. Now let's look at the 12th root of 7 to the fourth. Well, we can rewrite the radical using a rational exponent. This can be written as 7 to the fourth power raised to the 1/12th power. And then we can use the fact that we have a power to a power, the power rule for exponents, and multiply those exponents together. 7 to the fourth to the 1/12th power is 7 to the 4 over 12. When you multiply 4 times 1 over 12, you get 4/12, which can be simplified to 7 to the 1/3 power. And then we can rewrite this with a radical and write it as the cubed root of 7 to the 1st power, or simply the cubed root of 7. So our simplified answer for the 12th root of 7 to the 4th is the cubed root of 7. Now let's look at this last example. We have the square root of 5 times the 5th root of 3. Let's write them using rational exponents. So begin with the square root of 5, writing it as 5 to the 1/2 power. The 5th root of 3 can be written as 3 to the 1/5 power. We can't combine these as written because the bases are not the same. But if it was possible to get the exponents so that it would have a common denominator in the exponents, then it can be simplified. The LCD of the denominators of 2 and 5 is 10. So we want to make each of those exponents have the same denominator of 10. In the first fraction, 5 to the 1/2 power, we can multiply the denominator by 5 as long as we multiply the numerator by 5. And the result would be 5 to the 1/2 times 5 over 5 would be 5 to the 5/10 power. Our goal here is to write so that each exponent has a common denominator. 3 to the 1/5 power, the 5 being in the denominator, we would want to multiply by 2 to get that common denominator of 10, as long as we multiply the numerator by 2 as well. And that will give us 3 to the 1/5 times 2 over 2 would give us 3 to the 2/10 power. Now notice that we have the common denominator in the exponents. We can now write that as the 10th root, as a single radical. So let's write this as 10, the 10th root, of 5 to the 5th power times 3 to the 2nd power. And then we can further simplify this by writing it as the 10th root of 5 to the 5th times 3 to the 2nd, which when we multiply those out would be the 10th root of 28,125. All right, the Pythagorean theorem relates the lengths of the sides of a right triangle. If A and B are the lengths of the shorter sides of a right triangle, we also call those the legs, and C is the length of the longest side, which is the hypotenuse, then we have this relationship that a squared plus b squared is equal to c squared. The two shorter sides are the legs of the triangle, and the longest side is the hypotenuse. The hypotenuse is the side that's opposite the right angle. Thus, another way of looking at this is that leg squared plus leg squared is equal to the hypotenuse squared. In example 8, we're using the Pythagorean theorem to find the length of side A if we let b equal 5 and c equal 9. Now the Pythagorean theorem says that a squared plus b squared is equal to c squared if a and b are the legs of a right triangle and c is the hypotenuse. So if we know that a is our unknown, b is the other leg, we're going to say b is equal to 5, and the hypotenuse is c. c is equal to 9. By substituting our known quantities, we get a squared plus b squared, which is 5 squared, is equal to 9 squared. Let's simplify by evaluating the exponents for the 5 and 9, and we'll get a squared plus 25 is equal to 81. Let's solve this equation for a by subtracting 25 from both sides of the equation, and we get a squared is equal to 56. Now to solve for a, if we have a squared equals 56, the way to get rid of that power of 2 is by doing the inverse of raising to the second power, which is finding the square root. We're going to take the square root of the left side as long as we take the square root of the right side. So we get a, the length of side a is the square root of 56. Now that's not a perfect square, so it doesn't work out to be a nice whole number, but we can simplify the radical to find the length of leg A. We can use a factor tree, and we know that 56 is the same thing as 4 times 14, and 4 is the same thing as 2 times 2. 14 is the same thing as 2 times 7. With square roots, we're only taking out perfect squares, or those pairs of 2 factors, and that comes out as a single 2 in front of the radical, and the 2 and the 7 left under the radical can be multiplied together to give you 14. So the length of the leg A is equal to 2 square root of 14.